Section 6.4, Best Approximation, Least Squares. First we have our best approximation theorem. If W is a finite dimensional subspace of an inner product space V, and if B is a vector in V, then the projection of B onto W is the best approximation to B from W in the sense that the length of the vector B minus projection of B on W is less than the length of the vector B minus W for every vector W in W that is different from the projection of B onto W. What this theorem is essentially trying to solve is the problem where we have AX equals B for some inconsistent system where we don't actually have a solution X that will fit. So what we try to do is we look at the difference between AX and B in the sense of the Euclidean norm, so we'll look at the length, and we try to make this value as small as possible, because if this value is equal to 0, then X would be a solution. We don't actually have a solution because it's inconsistent, so we figure, okay, we'll find the closest thing to a solution if there was one, which is whatever would make this value the smallest. So that's where this theorem comes in, which tells us that the smallest vector will actually be B minus the projection of B onto W for B minus W. So let's prove this real quick. For every vector W in W, we can write B minus W as B minus the projection of B onto W plus projection of B onto W minus W. So we're just subtracting and adding this vector right over here, and that's the same thing as just adding 0, so it doesn't change it. This is still B minus W. But the projection of B onto W minus W, it being a difference of vectors in W, is itself in W. And since B minus projection of B onto W is orthogonal to W, the two terms on the right side of the equation are orthogonal. Thus, it follows from the theorem of Pythagoras that the length of B minus W squared is equal to B minus projection of B onto W squared plus projection of B onto W minus W squared. So if W is not equal to the projection of B onto W, it follows that the second term in this sum must be positive, so that has to be positive, and hence that B minus projection of B onto W squared must be less than the length of B minus W squared. So if this is positive, then what we have left must be less than that. Since norms are non-negative, it follows that we can get rid of the square root. We can basically take the square root of each one. So we get that the length of the projection of the length of B minus projection of B into W must be strictly less than the length of B minus W. For every linear system, AX equals B, the associated normal system, A transpose AX equals A transpose B, is consistent, and all solutions are least square solutions of AX equals B. Moreover, if W is the column space of A and X is any least square solution of AX equals B, then the orthogonal projection of B on W is projection of B on W equals AX. So we're basically saying that we're going to come up with a least square solution, in other words, an approximate solution to the system, in the sense that we can now figure out approximate solutions for inconsistent systems. That's really the motivation here, and we're going to take advantage of the previous theorem in order to do that. So let's do an example real quick. We'll find the least square solution, we'll find the least squares error vector, and the least squares error of the linear system given. So first we'll write out AX equals B. So A is just the coefficients, so 1, minus 1, 3, 2, minus 2, 4, and B is 4, 1, 3. So let's look at A transpose A, so we can use the previous theorem. So A transpose A is 1, 3, minus 2, just take that column, make it into a row, and minus 1, 2, 4, multiplied by a, which is 1, 3, minus 2, minus 1, 2, 4. So doing the multiplication, we get 14 minus 3 minus 3, 21. Let's get A transpose B now. So that's 1, 3 minus 2 minus 1, 2, 4 multiplied by B, which is 4, 1, 3. And we get 110. Okay, so now let's write out the equation A transpose AX equals A transpose B. So that's 14 minus 3 minus 3, 21 times, how about for X, we make it X1, X2. And we'll set that equal to A transpose B, which we computed as 110. So then let's see if we could solve this system. How about I divide the first row by 14, so I'll get 1 minus 3 over 14. And this 1 I'll adjoin, so I'll get 1 over 14. And then I'll keep the second row, minus 3, 21, 10. Okay, let's keep going, and let's get a 0 underneath. So I'll keep the first row, 1 minus 3 over 14, 1 over 14. But for the second row, I'll subtract 3 times the first, or I'll add 3 times the first, and I'll get 0. 285 over 14, 143 over 14. And then I'll multiply this row by this reciprocal in order to get a 1 over there. So I'll get the same top row, 1 minus 3 over 14, 1 over 14. But for the bottom row, I'll get 0, 1, 143 over 285. Then I'll keep going, and I'll get a 0 above that 1. So I'll just add 3/14 times the bottom row. I'll get 1, 0, 17 over 95. And then 0, 1, 143 over 285. Okay, so now we've solved ATAX equals A transpose B. So we see that X1 is equal to 17 over 95, and X2 is equal to 143 over 285. So now we can approximate B minus AX. So we have B minus AX is equal to 4, 1, 3 minus 1, 3 minus 2 minus 1, 2, 4 for A, and then we're plugging in this X, which is 17 over 95, 143 over 285, and that equals, let's simplify a little bit, 4, 1, 3 minus 92 over 285, 439 over 285, and 94 over 57. And then subtracting, we get 1232 over 285 minus 154 over 285 and 77 over 57. So all we need to do is get the length of that, and we have our approximation, so that means the length of b minus ax. If we take the square root of each of these squared, add them up, so we get approximately 4.556. So we found the least squares solution. Our least squares solution was what we got from over here, where we had x1 equals 17 over 95 and x2 is 143 over 25. We found the least squares error vector. That was b minus ax. That's equal to this guy. And then we found the least squares error. That was the last thing we did by just finding the length of the least squares error vector. How about we do another example? Let's find the least squares solutions, least squares error vector, and least squares error of this linear system now. So again, we'll write out ax equals b. So in this case, we have a equal to 3, 2, minus 1, 1, minus 4, 3, 1, 10, minus 7, and we have b equal to 2, minus 2, 1. Let's look at A transpose A. 11, 12, minus 7, 12, 120, minus 84, minus 7, minus 84, 59. If you do the multiplication, A transpose B, if you do that multiplication, I'm not going to do it for you, is 522 minus 15. Sorry, but I'll just run out of space. Then let's do A transpose AX equals A transpose B. So we get 11, 12, minus 7, 12, 120, minus 84, minus 7, minus 84, 59, and I'll adjoin that with 522 minus 15, and I'll solve that system. So what we can do is subtract off, divide, do basically the same thing we did last time. It turns out that the reduced row echelon form will end up being 1, 0, 1/7, 2/7, 0, 1, minus 5/7, 13 over 84, and the last row becomes all 0. It just takes a little while to reduce it, or you could use a calculator. In any case, we see that for our least squares solution, we get x1 equals 2/7 minus 1/7 t. x2 equals 13 over 84 plus 5/7 t. And that means that x3 is our parameter t, just from that third row of zeros. So we have our least squares solution. Let's find out how far off it is, but let's look at our least squares error vector. So that's b minus ax, which equals 2, minus 2, 1, minus 3, 2, minus 1, 1, minus 4, 3, 1, 10, minus 7, times 2/7 minus 1/7 t, 13 over 84, plus 5/7 t, and t. Okay, so simplifying a little more, we get 2 minus 2, 1, minus 7, 6, minus 1/3, 11, 6. And that ends up becoming 5, 6, minus 5/3, minus 5, 6. Let's get the error now that we have the error vector. So we'll take the length, and we get 5, 6 squared plus minus 5/3 squared plus minus 5, 6 squared. Take the square root, and it equals 5, 6 rad 6. If A is an n by n matrix, then the following are equivalent. The column vectors of A are linearly independent, and A transpose A is invertible. We'll use that theorem, but we won't prove it. If A is an n by n matrix with linearly independent column vectors, then for every n by 1 matrix B, the linear system Ax equals B has a unique least square solution. The solution is given by x equals A transpose A inverse A transpose B. Moreover, if W is the column space of A, then the orthogonal projection of B on W is equal to AX, which is this quantity over here from before, A transpose A inverse A transpose B. How about we use this theorem now to find the least square solution of the linear system in example 1. So what we'll do is we'll write out x equals A transpose A inverse A transpose B instead of the least square solution that we got before. So this is an alternative. We'll do 14 minus 3 minus 3, 21, and we'll take the inverse of that, and we'll multiply that by 1, 3, minus 2, minus 1, 2, 4, and then multiply that by B, which is 4, 1, 3. Simplifying, we get 1 over 285, 21, switch with 14, and then minus 3 is 3. So that's the inverse, and then we multiply that by 1, 3, minus 2, minus 1, 2, 4, and multiply that by B, 4, 1, 3. Doing all the multiplication, we should get 17 over 95, 143 over 285. And notice that's the exact same least square solution that we got in example 1, but we didn't end up having to solve any system in order to get it. We just had to do some multiplication. So that's kind of nice. We showed in section 3.3 that the standard matrix for the orthogonal projection onto the line W through the origin of R2 that makes an angle theta with the positive x-axis is p theta, given by this matrix. Let's derive this result using the theorem that we just used. So how about I draw what's going on here? So here would be my y-axis, and here will be the x-axis, and we'll put our line W going through the origin, and then we just need some projection onto there through an angle theta with the positive x-axis. So here will be my angle theta. So I will project onto W. I'll make W the vector with length 1, so this vector right over here will be W. So that means that the x-coordinate for W, if I go straight down, should just be the cosine of theta, and the y-coordinate for W should just be the sine of theta. So that means that W has coordinates cosine theta sine theta. So I'll make my matrix A equal to cosine theta sine theta. So now we can compute the least squares solution. So we'll do A times A transpose A inverse A transpose. That'll be equal to cosine theta sine theta times A transpose A inverse is actually 1 in this case. And then cosine theta sine theta is A transpose. It's a nice thing about the identities. Cosine squared plus sine squared equals 1. Simplify things a lot. Multiplying all this through, we get cosine squared theta sine theta cosine theta sine theta cosine theta and sine squared theta, which is exactly equal to p theta, as we have previously seen. So now we can add to our equivalent statements here. We have A transpose A being invertible is equivalent to all the rest. And we can end with the theorem that if A is an n-by-n matrix with linearly independent column vectors, and if A equals QR is a QR decomposition of A, then for each B in Rm, the system Ax equals B has a unique least squares solution given by R inverse Q transpose B. This kind of makes sense in the context of what we're doing, since we would expect the least squares solution to be x equals QR transpose times QR, and then we take the inverse, multiply that by QR transpose B, but that's the same thing as writing R transpose Q transpose, right? We just take the transpose and put them on each one and flip the order, multiply that by QR, and take that inverse, multiply that by QR transpose B, but then we can do the inverse applied to these guys. We just again move the order, so we get R inverse R transpose inverse R transpose Q transpose, right? We take the transpose, put it on B, because of all the cancellation. So again, cancel some more, we get R inverse Q transpose B, which is exactly what the theorem is telling us.